Alright, let's take a look at the story problems from the notes here. So this first one just says, the population is increasing at a rate of 3% per year. If the present population is 20,000, what will the population be at the end of 5 years? Okay, so if you look back on the other side of the notes, we had two forms for our geometric term. We had the one we've been using is a sub n equals a sub 1 times r to the n minus 1 power. And the other one, listed right beside it, is a sub n equals a sub 0 times r to the n power. Okay, now these are very, very similar formulas. It just depends on the information we're given. So in all the lists of numbers that we've been given, we start with a first term, okay, and then we continue going. In a lot of story problems, though, we are given an initial value, okay, something that we kind of want to think of as our 0th term. That's the case in both of these story problems, actually. So this first one, it says our present or initial population is 20,000. That's what we're starting with. Okay, that's not our after 1 year in this case. That's at year 0, the population is 20,000. So that tells me I want to use this formula right here. So my a sub 0 is going to be 20,000. Okay, so I'm going to say a sub n is 20,000 times, now r, okay, the rate at which the population is growing, we don't want to think about just the 3%. Okay, if I'm increasing at a rate of 3%, this is really going to be, I'm going to take this number and multiply it by 103%, which as a decimal would be 1.03, and then that will be raised to the n power. So if I want the population at the end of 5 years, I want a sub 5, and that'll be 20,000 times 1.03 to the 5th power. And let's get the calculator up for that. So 20,000 times 1.03 to the 5th power gets me about 23,185. So since in this case we're talking about people, okay, it makes sense to round to the nearest whole number. Right? We're not going to say we have 0.48 of a person. So the key differences on the story problems here from what we've been doing, usually, and I mean there are some cases where this isn't true, but most of the time we're going to want to use this formula because we're given an initial value. Okay? And then if we're thinking about percentages, okay, especially in this case, if that percentage is increasing, I need to say, well, that's going to be 100% of whatever my value was plus this 3%, which would be 103%. Okay, so let's take a look at the other one here. It says a radioactive isotope is decaying at a rate of 18% every hour. Currently, there are 250 grams. So that 250 grams is like my initial value. So I'm going to be using this formula, a sub 0 times r to the n power. So to first write my formula, I'm going to say a sub n equals a sub 0, which we said was 250, times my r. Now, we're saying we're decaying at a rate of 18%. That doesn't mean that I'm going to be left with 18% of the substance after an hour. That means I'm going to be left with 82% of the substance, right? 100% minus 18%. So the rate that we're actually going to put in here, or the common ratio, is actually going to be 0.82, 100% minus this 18%, and that'll be, or I'm sorry, minus this 82%, and that'll be raised to the n power. So then if I want how much is going to be left 1 day from now. Our rate was in hours though, so 1 day later is 24 hours later. So 250 times 0.82 raised to the 24th power, and that will be 250 times 0.82 to the 24th power. Not very much left. 2.135 grams. Okay, so give the homework a try, and we will talk about it tomorrow.